multi-size representation for images that supports continuous resizing. An image can be shrunk in a non-uniform manner while preserving its features, but it can also be extended beyond its original size. Instead of scrolling through images that do not fit in a given display, we gracefully resize them to fit inside the window. To illustrate another application for this tool, we show a simple object removal procedure. By adding negative weights to the energy of an image, the user can attract the seams to pass through specific areas first. By reducing the size of the image, these areas are removed first, in effect erasing them. To retain its original size, the image is enlarged by using seam insertion. Note that this technique changes the whole image and does not simply erase the objects marked. More examples can be found in the paper and the supplemental materials.
We present a system for inserting new objects into existing photographs by querying a large image-based object library, pre-computed using a publicly available Internet Object Database. In this video, we will generate a composite image with our system. After selecting a background image and specifying its horizon line, the user can browse the object library by using a hierarchical menu. The objects in the side panel are sorted by how well they match this particular scene. After selecting an object from the panel, a single click pastes the object at the desired 3D location, and automatic segmentation and blending is performed. Alternatively, the user can first select the desired 3D location to paste an object, and then choose among the objects that best fit that particular location. It only takes a few mouse clicks to generate a realistic image composite.
Contrast, Soft Scissors is an interactive tool for extracting high-quality mattes in real time. Alpha values are computed as the user draws a scissoring stroke along the foreground edge. Our system simultaneously computes the foreground colors and gives the user a new composite. The feedback makes it easy for users to quickly extract the foreground object.
Painterly styles created in our system. This landscape scene contains several cow and horse models, a terrain, and a distant skybox, each rendered with our hatching shader. Each object in the scene is rendered as a single patch. As long as the camera moves gradually, the patterns move plausibly and have striking cartoon-like quality. This still life demonstrates our Painterly style. Again, each object is rendered as a single patch. This running figure is divided into patches along natural texture boundaries and rendered with several halftone styles. Here we use multiple patches and blended across patch boundaries.
The system automatically chooses the best saved viewpoint and creates a labeled cutaway illustration that exposes the target. The user can also select multiple target parts. For each set of targets, the system chooses the most appropriate viewpoint. We have tested our system on CAD models as well as anatomical datasets, like the one shown here. If, as part of the authoring process, the user has organized parts into logical groups, the viewer can expose each group in order with a single click, as shown here. During the brief pause after the user selects a new set of target parts, the system chooses the best viewpoint, computes cutting parameters, and determines how to arrange text labels, before smoothly animating to the solved cutaway illustration. In addition to automatically exposing parts, the viewer can directly manipulate the cutting parameters of individual cuts. Here, the user draws a stroke to open up a cut, and then interactively modifies its size and position. Finally, we show that our system can generate effective cutaways of an engine model that contains well over 100 individual parts. In this video, we have demonstrated our system for creating and viewing interactive cutaway illustrations of complex models. Thank you for watching.
We now show an example modeling sequence. As you see here, the user interactively performs sketching operations, and the system continuously generates a 2D pattern and shows the 3D model as a result of the simulation. This guarantees that the 3D model on the screen is a good estimation of the actual plush toy model created from the 2D pattern. Using the system, even a novice user can create his or her own plush toy model. This is the result of the 3D model. Here is a result of actual sewing. We also created a balloon from the pattern.
These results are obtained at the fraction of the computational expense, and as these sequences show, this fast projection method gives qualitatively similar results. Our method can easily be integrated into an existing cloth solver using a velocity filter approach. Robustly handling complex scenes such as this ballet sequence or the following runway scene. Notice how our method maintains constraints without dissipating the motion of the cloth, resulting in a lively and responsive simulation.
Of 22,500 particles in total deforming using our method. In this scene, penguins collide with icicles but not with each other. The deformation in this scene can be processed at real-time rates, 25 frames per second on a typical desktop computer.
of an SUV that we took with a handheld camera, and we want to build a 3D model of it. To begin, we start roughly tracing out the basic structure of the car in one image. Lines turn green as they snap to the edges, and an initial 3D model is generated, as we can see when we move to another frame of the video. In this new frame, we can adjust the model and trace more structure. We can also draw curves and generate surfaces from them. Now the existing model can be mirrored about a plane, which is specified by tracing lines over the model. This allows you to model parts of the scene not visible in the video. Now we can take a curve and extrude it to model a solid like this tyre. We now have a 3D model which is shown in wireframe here, and which we can use to manipulate video in ways that wouldn't otherwise be possible.
The results of applying both the advected pigment texture and the abstraction steps to the original video. We have also matted the edges of the video to enhance the illusion of watercolor. Here are some additional results on other video sequences.
That's mostly the aspects.
Mr. Ackerman doing VR. This is virtual head. That's a camera. That's him being a doorknob.
I'm just seeing a white flashing light and nothing else.
This is an internal projection sphere. Can be fed off a computer. So we're thinking infosphere in the lobby, or tracking our planes. Only about $50,000 though. Motion tracking software. Motion capture for 5,000. It's cage TV, it's pretty cool. It's a 3D printer.